Dear grade 12 student, we are going to do a practice about our chapter recall of function. Let's, let's start by the first exercise. Consider the function g of x equal x6 minus 6x3 plus 5. It's a polynomial function. Then it's defined over R, open interval minus infinity plus infinity. But in this question, we need to study only the second part of its domain. I mean 0 open to plus infinity. The graph of g of x as shown is given. The first question is to show that g of x equal to 0 has a unique solution alpha such that alpha belongs to an open interval 1.5 to 2. What I mean by g of x equal to 0. G of x equal to 0 is the intersection between the curve of the function g and x-axis. Now let's start by the solution. G of x equals 0 has the unique solution. We have 3 steps. First step, the function must be defined and continuous over the given domain. So g of x, it's a polynomial function, then normally it's defined and continuous over 1.52. Second condition, the function must be monotonic. It means that increasing or decreasing over the given domain. Using the graph, we see that the graph of the function g of x from 1.5 to 2 is an increasing graph. Then g of x strictly increasing over 1.5 to 2. This is the second condition. And the last condition, the multiplication of g of 1.5 by g of 2 must be negative. We see that g of 1.5 is below the x-axis, then g of 1.5 negative. And g of 2, it's above the x-axis, positive. Then the product of these two numbers are negative. Then the 3 conditions complete. So g of x equals 0 has the unique solution alpha such that alpha between 1.5 to 2. And this is the place of alpha in the figure. So g of x equal to 0, it means the intersection between the curve of the function g of x and the x-axis. And the abscissa of the intersection point is alpha. Now let's go to the second question. Set up the table of variation of g of x. Normally, we need to use the graph of g of x to study to set up the table of variation of g of x. But we need to start from 0 to plus infinity. So from 0 to 1.5, the function is decreasing function. And from 1.5 to plus infinity, the function is an increasing function. So from 0 to 1.5, the function is a decreasing function, then the derivative is negative. At 1.5, the function has a minimum extremum, then the derivative is equal to 0. And finally, from 1.5 to plus infinity, the function is increasing, so the derivative is positive. To complete the table of variation of g of x, we need to put the image of this point and the limit of g of x under plus infinity. So g of 0 is equal to 5, g of 1.5 is equal to minus 4, and the limit under plus infinity of g of x equal to plus infinity. Final question is to study the sign of g of x over its domain. Normally, we want to use also the figure. From 0 to 1, the curve of the function g of x above x-axis, so g of x positive. From 1 to alpha, this point, using the first part of this question, is alpha. So from 1 to alpha, the function is below the x-axis, so it's negative. Finally, from alpha to plus infinity, the curve of this function is above the x-axis, then the function g of x here positive. Conclusion: if x belongs to 0, 1, union alpha plus infinity, g of x positive. And if x belongs to 1 alpha, g of x negative. And finally, at x equal 1 or at x equal alpha, the function is equal to 0. Now let's go to the second exercise. Part A, consider the function g of x equal to x cubed plus 3x minus 2 defined over 0 plus infinity. Determine limit plus infinity of g of x and g of 0. Determine g prime of x and set up the table of variation of g of x. Show that g of x equals 0 admits on 0 plus infinity a unique solution alpha such that alpha belongs to 0.4, 0.6. Last question is to deduce the sign of g. Now let's start by the first question. It's to determine limit plus infinity of g of x. G of x is a polynomial function, then the limit plus infinity of g of x, it's equal to the limit of the highest degree of g of x. It means that the limit of x cubed is equal to plus infinity. G of 0, simply we replace x by 0, we get g of 0 equal to minus 2. Now let's go to the derivative of g of x. Simply g prime of x is equal to 3x2 plus 3, and it's positive for every x belongs to 0 plus infinity, then g is an increasing function. Now put the table of variation of g of x, x from 0 to plus infinity, g prime of x positive, then g of x is an increasing function. From minus 2, the image of 0, to plus infinity, the limit of g of x under x plus infinity. Now the second question is to show that g of x equal to 0 has a unique solution alpha over interval 0.4, 0.6. As x belongs to 0 plus infinity, g of x defined and continuous since it's a polynomial function, and by using the table of variation of g of x strictly increasing from minus 2 to plus infinity. And since 0.4, 0.6 included in 0 plus infinity, then g of x defined and continuous and strictly increasing also over this interval. And by replace x by 0.4 in the function g of x, we get g of 0.4 equal to minus 0.73, normally by using the calculator, and g of 0.6 equal to 0.016, then g of 0.4 negative and g of 0.6 positive. So the three conditions of the question g of x equals 0 has a unique solution is complete, defined, continuous and strictly increasing, and g of 0.4 negative and g of 0.6 positive, then g of x equals 0 admits on 0 plus infinity a unique solution alpha where alpha belongs to 0.4 and 0.6. Remark, alpha make g of x equal to 0, then g of alpha equal to 0. Now deduce the sign of g of x. The sign of g of x, we need to put alpha in the table of variation of g of x. So 0 alpha plus infinity g prime is positive, as we know, and alpha make g of x equal to 0. The image of 0 is minus 2, and plus infinity limit of g of x plus infinity, it's equal to plus infinity. By using this table, from x belong to 0 to alpha, g of x, it's from -2 to 0, then it's negative. And when x equal to alpha, g of x equal to 0, from alpha to plus infinity, g of x, it's from 0 to plus infinity, it's positive. So the conclusion is, as x belong to 0 alpha, g of x negative, and as x belong to alpha plus infinity, g of x positive. Now part B of the second exercise. In this part, take alpha equals 0.5 and consider the function f defined by f of x equal x plus 2 plus 1 minus 3x over x2 over 0 plus infinity. First question is to determine the limit of f at the upper boundary of the domain of f. Second question, part A, shows that dy equal x plus 2 is an oblique asymptote of c as x tends to plus infinity. B, study the position of c and d. 3, show that f prime is equal to g of x over x3 and set up the table of variation of f. And finally, we need to construct d and the curve of the function f. Now let's start by calculate the limit at infinity of f of x. Limit infinity of x equal to limit infinity to x plus 2 plus 1 minus 3x over x2. It's equal to limit x plus 2 take the highest degree of the numerator and the highest degree of the denominator, and by simplification we get limit x plus infinity x plus 2, we take the highest degree x plus minus 3 over x, and by replacing x by infinity we get plus infinity plus minus 3 over plus infinity, and this is equal to 0. Then the limit plus infinity to f of x, it's equal to plus infinity. Now let's calculate the limit under 0 plus of f of x. Simply replace x by 0, we get 2 plus 1 over 0 plus, it's equal to 1, 2 plus infinity. Then x equals 0, it's a vertical asymptote since limit at number get plus infinity, so x equals this number is a vertical asymptote. Now we need to show that dy equal x plus 2 is an oblique asymptote of c. First, let's find the expression of f of x minus y of d. F of x minus y of d. Replace f of x by its expression x plus 2 plus 1 minus 3x over x2 minus x plus 2. Simplify x plus 2 by x plus 2. We get 1 minus 3x over x2. The question is to show that d is an oblique asymptote of c as x tends to plus infinity. So we need to calculate the limit plus infinity of f of x minus y of d. It is the limit of this expression. Take the highest degree and by simplification we get limit plus infinity minus 3 over x. It's equal to minus 3 over plus infinity equal to 0. Then dy equal x plus 2 is an oblique asymptote of c as x tend to plus infinity. Now we need to study the position of c and d. In this part, we need to study the sign of f of x minus y at d. It means the sign of the expression 1 minus 3x over x2. Finding the root of the numerator 1 minus 3x equal to 0. Simply for x equal to 1 over 3 and x2 positive for every x belong to 0 open plus infinity, x must be different than 0. Now put the root in the table. X, the domain 0 to plus infinity. We have only one root, it's 1 over 3. And the sign of the expression 1 minus 3x over x2 is related only by the sign of 1 minus 3x since x2 positive. But we need to shade the part here at 0. Then 1 minus 3x. If x from 0 to 1 over 3, the sign of 1 minus 3x positive. And at 1 over 3, 1 minus 3x, 0. And from 1 over 3 to plus infinity, the sign of 1 minus 3x negative. We can take number between 0 and 1 over 3 and replace it in 1 over minus 3. The result is positive. And we can take number also here from 1 over 3 to plus infinity. By example 1, the result is negative. So, from 0 to 1 over 3, f of x minus y let d, it's positive. Then the position C above D. At 1 over 3, we have an intersection C cut D at point 1 over 3. We can replace 1 over 3 in the expression of f of x or y let d. Simply in y let d, we get 2.3. And from 1 over 3 to plus infinity, we have f of x minus y of d negative. Then the position C below D. Now determination of f prime of x. F of x, it's equal to x plus 2 plus 1 minus 3x over x2. Then the derivative of x, it's 1. The derivative of 2, it's 0. And 1 minus 3x over x2 in the form of u over v. The derivative of this expression, the composite function, it's u prime v minus v prime u over v squared, where u equal 1 minus 3x and v equal to x squared. So the derivative equal to 1 plus u prime, it's minus 3, v it's x2 minus the derivative of x2 is 2x times 1 minus 3x over x2 power 2. And by calculation, we get f prime of x equal gx over x3. Be careful to take x common here. Now we need to study the sign of f prime of x. The sign of f prime of x is related to the sign of g of x and of x cubed. So we need to put the table of x and gx and x cubed and deduce the sign of f prime. X, it's from 0 to plus infinity. We know that alpha make g of x 0 and the sign of g of x before alpha is negative and after alpha is positive. This is the relation between the two parts of this question. In the part A, the last question of the part A, we deduce the sign of g of x and we need to represent this sign of g of x in the table of the sign of f prime because there exists a relation between f prime and g of x. It means we need to use this sign. The sign of x cubed from 0 to plus infinity, it's also positive. It's positive for every x. So from 0 to alpha f prime negative and at alpha f prime equal to 0, and from alpha to plus infinity the sign of f prime it's positive. This is the tip of sign of f prime. Now we need to set up the table of variation of f. X from 0 to plus infinity where alpha is 0.5. From 0 to 0.5 derivative is negative, then the function is decreasing. At 0.5 we have derivative equal to 0, then we have an extremum. From alpha to plus infinity the derivative is positive, then the function is increasing. Limit of f of x at 0 it's plus infinity, and limit of plus infinity is equal to plus infinity. Last question, we need to draw the graph of f. We need to use all the result before the question 4. I mean that dy equal x plus 2, it's an oblique asymptote. We need to draw it by taking 2 points. A1 over 3, 2.A3 is the intersection between C and D. X equals 0 is the vertical asymptote, and we need to put finally the minimum extremum point 0.5, 0.5. Then my function f of x is decreasing from plus infinity to the minimum. Be careful that x equals 0, it's a vertical asymptote. And then my function is increased from this extremum minimum point to plus infinity. Be careful about the oblique asymptote.